Hello and welcome to EP2CM4 topic number 7, piezoelectricity. This week we're going to look at piezoelectricity, which is another internal source of strain, like thermal expansion, but unlike externally applied stresses. That's what we call an external source of strain. Piezoelectricity is the coupling of a material's electric and charge displacement fields to its stress and strain fields. So this means that electric fields or charge displacements are going to cause stress and or strain, and vice versa. You can have stress and strain causing electric fields and charge displacement. You can have charge displacement and electric field causing stress and strain. Where is this used? Well, it's used in the special materials where it occurs to move things electrically with extreme precision, like in a piezoelectric actuator, to have temperature-independent resonators robustly keep time. This is like a quartz crystal resonator that shows up in watches, in phones, and computers. That's fundamentally the electrical mechanical connection that's allowing it to keep time so precisely, rather than just using an electrical resonator, to turn mechanical force that you can apply with your finger into a high enough electric field to make a spark, like in a click barbecue lighter, and to transfer between sound energy and electrical energy and microphones and speakers and a number of other applications. Check out the Wikipedia page on piezoelectricity. There's more and more all the time. So we've already seen how stress leads to strain through the compliance matrix, which has the wrong symbol here. That should be an S. Yeah, compliance matrix is the one for S. We've seen how stress leads to strain through the compliance matrix, and we've seen, this is Hooke's law, right? You push on it more and it's going to move more depending on how compliant the material is. Stiffness would have been on the other side. And we've seen how temperature change can cause strain directly. We called this the thermal strain last week. And in some special materials, electric fields will also cause strains themselves. So you apply an electric field. This doesn't happen for all materials, but for some subset of piezoelectrics, we'll see what's required. Sorry, some subset of dielectrics, I should say, are piezoelectrics. And that means that when you apply an electric field, if it's the right kind of electric field, not necessarily every direction, but the right direction of electric field, then it can cause strains in the material, where D here is the 3x6 piezoelectric coupling coefficient matrix. D, with the T up there, that means matrix transpose. So that turns it into a 6x3 matrix by flipping it about the diagonal. So here's an example of that. Here's a D matrix for PZT5A, a common crystal that has a pretty high piezoelectric effect. And when you transpose it, it goes over to this. So you keep this 0 the same, and you flip this one up to the top row. The first column becomes the top row there, and then second column, second row, third column, third row, etc., etc. Okay, then we're going to matrix multiply this over here, and you'll remember, why are we doing that? Oh, we're just going to calculate what this is, what the piezoelectric strain is for this PZT crystal, at least something that has this. If we apply an electric field, then we're going to get a strain, which is given by D transpose times E. So we multiply this row by this column. The picometers per volt, we don't need that. That's just a scalar. So you could imagine it multiplies by every single element here. It stays in those elements during the transpose, and you can pull it back out again, or we could put it on the left side, etc. Let's just take this row, multiply by that column. Don't worry about the constant. It can move around. And what we're going to get is 0 times EX plus 0 times EY minus 171 times EZ. And that's our new first row. Second row, same thing. And we're going to get negative 171 EZ again. Third row, 0, 0, and then positive 374 EZ. Then the next one is going to be a 584. This is in the middle, so that means it's going to be giving us the Y component there. And the first one here, the fifth row, tells you that 584 EX is responsible for, in Voigt notation, fifth row is the XZ shear strain, and there's no XY shear strain producible by electric fields in PZT5A from the piezoelectric effect. So, okay, what do we have here? We have Z fields. EZ seems like, because of these components, the components in the first three rows, are the ones that would tell you electric field is giving you axial strains. The components in the last three rows of D transpose would tell you that electric fields can create shear strains. So EZ creates only axial strains in an unconstrained piece of PZT5A. A constrained piece of PZT5A would possibly, depending on how it's constrained and what its other matrices have, one of these axial strains maybe would cause shear if we stop it from being able to be expressed. Like if you constrain it in Z, then maybe when it tries to do this straining, it would cause some shear depending on what else is going on in the matrix components. We don't know yet. We're going to need to look at the stiffness and compliance matrices, stiffness or compliance matrix really, to figure that stuff out. But at least for now, when in an unconstrained piece of PZT5A, the strains that show up directly from applying electric fields are the ones you get by taking D transpose and multiplying it across by E. So that's what this is telling us. We've got Z fields giving us axial strains, Y fields give us YZ shear strains, and X fields give you XZ shear strains. So that's specific to PZT5A, but other materials with different piezoelectric coupling coefficients will couple different fields to different strains. So for instance, single crystal alpha quartz, that's the famously piezoelectric kind that's used in watches and all kinds of things for timekeeping. Alpha quartz has this D matrix, and if you take the transpose of this and then multiply it out by the arbitrary electric field vector that we've got here, you find that the strain is negative 2.3 EX, 2.3 picometers per volt EX in the X direction. We've got Y-directed strain, which is positive 2.3 of that same thing. And we've got no Z-directed strain. But we do have shear strains in all three directions based on the X field for gamma YZ, the first one still, same order of strains in the strain vector. And then gamma XZ is based on the Y-directed field, while gamma XY is based on the Y-directed field. So in quartz, we've got the X fields as the ones that give us axial strains, but they can't give Z axial strain. And we do have that same field that gives axial strains also giving a shear strain. That didn't happen for PZT. And we have a different strain in X and Y, whereas here they were symmetric. And we have Z fields doing nothing, while in PZT, each of the fields did something, caused some strain directly, not the same for quartz. So clearly there's some pretty weird crystal stuff going on under the hood here, and there's a lot of variety in what kind of piezoelectric materials and effects you can get. Let's do an example. We've got a mechanically free slab of PZT5A that has these dimensions, 5 centimeters in X, 1 centimeter in Y, and 1 millimeter in Z, and has gold electrodes on the top and bottom of its Z surfaces. This one's going to be set to 100 volts up here, and this one's set to 0 volts down there. And we want to figure out what the strains are that show up in the slab as a result. All right, well, strains in PZT 5A are set up by this matrix multiplication that we did earlier. So we've got the strains come from D transpose times the electric field, and in PZT 5A, that gives us this. So we're going to have fields in Z creating axial strains according to this, and fields in Y and X creating some shear strains. But what is the field that gets set up from this voltage distribution? Well, electric field is negative the gradient of the voltage, and voltage is only changing in the Z direction here. So that's going to mean that it is, let's put a smaller vector, 0, 0, and something in Z. And here it is dV by dZ, what the slope is of V in the Z direction. All right, so that is a change of 100 volts per a step down. It goes down by 100 volts per step down in Z, or it goes up by 100 volts per step up in Z of 1 millimeter. So with that negative sign still in front, we've got a 100 volt change, putting a space before the unit and then unit in not italic font, and a 1 millimeter distance. So if we get rid of the column vector notation because it's so sparse, there's a lot of zeros in there, that is, we're left with minus 1 times 10 to the 5 volts per meter. Okay, so if we take this one and we substitute it in for the Z, right, there's still a vector notation there if we want to get rid of the column vector notation. This looks like this is a scalar, so we need to say a Z hat there. Yeah, that's in the Z direction. Okay, so we substitute that in here for just the z's, and we are left with a new vector, 6 by 1, whose components are now unitless because we had picometers per volt, and we're going to multiply by volts per meter. So the meters per volt will cancel with the volts per meter, but the pico, E minus 12, we're going to have to account for. So this is 171 E minus 12 multiplied by 1 E minus 5, and we're going to get a, so 10 to the negative 12 times 10 to the 5 is going to be 10 to the negative 7. So this will be positive now because the negative 171 cancels with the negative 1 E5. Positive 171 E minus 7. So 171 times 10 to the negative 7. Here, same thing, 171 E minus 7. But this one now we're going to create a negative. So minus 374 E minus 7. And then 0 for the rest of them because we don't have any y field or x field. All right, so that is the set of strains. Strain is unitless, so that checks out. That's the strains that get created in this slab of PZT as a result of this voltage that's there. So just by applying 100 volts on the top versus 0 on the bottom, we put on this voltage. This is a stiff material. It's not like a Coulomb attraction here or something that's causing the plates to move together. It's moving around. Well, actually, I guess it ultimately is a Coulomb attraction, but not just this charge on this plate and this charge on this plate compressing the plates together, compressing the material. This is a different effect. It's moving around the atomic cores to allow things to move to create this strain directly from electric field. How does this lead to new dimensions? Well, you might remember from when we started this way back in the mechanics course that the strain leads to a change in length. A regular strain is a change in length over the original length. So if you want to know the new dimensions, you can say L prime is equal to the original length plus the change in length. And the change in length is L times epsilon. So this allows us to say that the new length is the original length times 1 plus epsilon. And this will be good as long as epsilon stays pretty small. Then we could even multiply these things together and cancel out some terms and figure out the volume from that. Okay, so since the original dimension was 5 centimeters in x, we'll take 5 times 171, E minus 7 centimeters will be the change in length, and then we add that to the original length, and we get the new length. Okay, so let's just go ahead and do that. Epsilon is equal to 171, negative 374, 0, 0, 0. Let's see if we can be somewhat systematic about that. Okay, get a little vector array thing there, and then we're gonna have the dimensions, maybe L, is equal to 5 centimeters. Oh, we'll say this times 1 E minus 7. 5 E minus 2, 1 E minus 2, and 1 E minus 3 it was. 0, 0, 0. Then we'll say L prime is equal to a sequence. We don't really need to put it back in a vector. So we'll just use the simple formula. Sequence of epsilon n times, let's say actually ln times 1 plus epsilon n. So the original length, that thing, times 1 plus the strain. Okay, and we'll do that for n is equal to 1 to 6. Great. So this is a pointwise, an element by element operation to multiply these elements by this element, written out kind of in raw code how you might do that. Right, so very small changes in each of the lengths that we originally had. By the way, if we want to put this back into a vector, then we could just say that we've got mod in the inside the vector brackets there. There we go. Okay, so we could call this L prime again, or we could have put the vector brackets around the sequence to begin with to get it to display like this. So where does piezoelectricity come from? Well, a couple of things that you need atomically for this to happen. You need charge asymmetry between atomic constituents. You need some things that are more positively charged than others. Maybe you need polar covalent bonding, where some of the atomic cores hold on to the electron effectively more strongly than other ones, or ionic bonding, where they do this kind of a lot stronger. The electron basically transfers from one atom to another one. And you need enough crystal asymmetry. You want these atoms to arrange themselves in a way such that when it strains, when you push on this and get it to compress, the positive and negative charges don't move in the same direction. So here's an example of what that might look like. You can see this hexagonal structure here is laid out so that when you compress it vertically, this one and this one, this negative charge and this positive charge move apart, but these positives and negatives up on the top don't move. So the thing is neutrally charged. There's just as much negative as positive, and yet when you compress it, it gets a polarization field. So this is a two-way process. This means that also if you were to apply a polarization field in this direction, then it would compress in the vertical direction. This is a hand-wavy way of hand-wavy view of where piezoelectricity comes from. But this is essentially the effect, right? You have atomic charge asymmetry, and you've got atoms arranging themselves in an asymmetric enough way to give this kind of overarching piezoelectric effect. Things move in different directions. The positive and negative charges move in different directions when you push on it. If you have things if you don't have the charge asymmetry, you can't have any polarization field, even if they move all in different directions here. And if you don't have a weird enough crystal structure that the positives and negatives move in different directions, then even if you have a pretty big charge asymmetry, you're not going to have any piezoelectric effect. Another thing that you need is large scale crystal grain alignment. I don't want to say that you need it to be single crystal necessarily, though that certainly helps. You need that all of the domains inside the material, all of the grains are oriented in roughly the same direction, or at least more oriented in the same direction, for you to be able to get a macroscopic piezoelectric effect. Otherwise, if maybe over on one half of the crystal they move and develop this polarization field, if right next door they develop a field in the other direction, and then it's totally random everywhere, there's no large scale polarization developed at all. Then you've got to have all of these things lining up and working together to create a net polarization field that you can see macroscopically. So here's an example. Quartz is a piezoelectric material. This is the chemical compound SiO2, silicon dioxide. And you might remember that oxygen is so electronegative that when we say something steals an electron from another atom in a chemical bonding process, we say that that thing that stole the electron has oxidized the other atom. So oxygen is a very electronegative atom, only less electronegative than fluorine, but I guess that's not as common in chemical processes as oxygen is, so we don't call it fluorinates. The other thing, we say that it oxidizes it. Maybe because we don't generally exist in a lot of fluorine gas, and oxidation is often very dramatic, and that's what burning is, right? So it's not always that dramatic, right? Like rusting is not nearly as exciting as burning, but it's also oxidation. Okay, silicon competing with oxygen doesn't have nearly the electronegativity, so doesn't hold on to those electrons quite as much. Now, from a quantum mechanics perspective, I am contractually obligated at this point to tell you that really we shouldn't say hold on to the electron, I suppose. It's a bit personification. Anthropomorphizing the elements is a taboo, right? So this is I should say that the quantum wave functions associated with silicon and oxygen bonding together, because of oxygen's higher electronegativity, will have a higher occupancy chance near the oxygen atom. So we're more likely to find the electrons closer to the oxygen, and the oxygen atoms are effectively more negatively charged than the silicon ones as a result. Or at least there's more negative charge near the oxygen atoms than there are near the silicon ones. Okay, so in addition to this, alpha quartz has a crystal structure which is trigonal. Now this is a a thing you can spend a lot of time on, understanding crystal structures. And I can't hope to do the thing justice right now, but here is a picture of the crystal structure of alpha quartz. The silicon are the gray things, and the oxygen are the red balls in this. And this is something that's very difficult to visualize. For now, I encourage you to go and find some better models that you can actually hold and see of the crystal structure of quartz to try and get a feel for what's going on there. Though I can tell you that when you look at quartz crystal as it naturally occurs, you can see that there's some pretty interesting structures there. Like it tends to cleave at strange planes, right? And almost looks kind of hexagonal from certain angles. So this is the perhaps a hint that quartz has some interesting stuff going on crystallographically. Definitely a rich topic. Look into it. For now, what we need to know is that because it's got enough crystal asymmetry and it's got charge asymmetry, we can have piezoelectricity. Okay, so that's enough of the hand wavy part of it. Now we're going to get a lot more mathematical. We can deal with electric fields, stresses, and charge displacements together using the full Piezoelectric Constitutive Equations. There's two different forms we're going to look at. The stress charge form, which is stress and then charge displacement field, and the strain charge form, strain and charge or electric displacement field as it's called. Okay, so these are equivalent forms. They just have different names for the coefficients inside. So we've already seen this a little bit. This is the stiffness matrix, C, and S, the compliance matrix here. If we have sigma equals C epsilon, then when we invert C, we have to have the thing that's in front of the sigma there be the same thing. So that's giving us epsilon is S sigma. We've seen that before. That's what we had earlier. And then earlier as well, we also had that the electric displacement field D in a linear dielectric is epsilon S times E. I should say at this point that this doesn't fully cover what's going on with all piezoelectric materials, because some piezoelectric materials are even weirder that they don't fully obey linear relationships here. We'll look at that a little bit later. Anyway, E and D are the piezoelectric coupling coefficient matrices. Epsilon S and epsilon T here are the things that go in front of the E field. So this is kind of confusing because we got epsilon doing double duty here. We have to always make sure to draw this vector if we keep wanting to use epsilon as the strain, because we also have the permittivity showing up again. So with permittivity being epsilon and strain being epsilon, we have to make sure to draw this vector on the strain so we don't get things confused. This is the piezoelectric coupling D matrix that we dealt with earlier, D transpose here, giving us the strain. But you can also write this using a piezoelectric coupling E matrix, and we'll see how these are related by combining these equations together. So that's another form of the piezoelectric coupling matrix you'll see. And there's a difference between the epsilon that's in the stress charge form and the epsilon that's in the strain charge form. We'll also see how to relate those together. If there's no stress or strain, no piezoelectricity, then we would just have that epsilon S has to equal epsilon T. So it must be that the thing that relates epsilon S and epsilon T goes away if the material is not piezoelectric. We'll see that again soon too. Because of this double duty of coefficients, a lot of treatments of this subject will not allow it. Having epsilon be both the permittivity and epsilon being the strain is sacrilege. So we can't have that. We're just going to redefine things, and we're going to use a capital S for the strain and a capital T for the stress, though this has its own problems if you start to build in things with temperature change, dealing with time in a case-insensitive thing like FlexPDE. So rather than go and completely redo all the previous stuff that we're doing, I'm going to try to keep us with these ones using the sigma and the epsilon vectors, and just always write the vector symbols. Hopefully it'll be clear from the context what we mean when we say epsilon, whether it's epsilon vector or epsilon the permittivity. Either way, if we, whatever syntax we use for this, if we know the electric field, maybe because we're applying the voltage somewhere, so we can just do what we did in the last example to find it out, then these equations are not coupled, right? You can just stick with the, maybe this one here, this form of it, and figure out what the strain is directly from the electric field, which is very similar to how we were incorporating thermal strain before. We said that it's the compliance multiplied by the stress plus alpha delta T for thermal strain. So if it's D transpose E, that's just another vector if we know what the E field is. So we can treat this just like thermal strain, except where the source of the strain is this applied voltage somewhere. If we don't know what the voltage is, then things get a little bit more complicated, because we're going to have to use what we know about the D field having a divergence, which is the charge density, to then figure out what the E field is and work out what the voltage is through that, or how to relate it to the other equation through that. Now, previously, we would say that the divergence of D field is the free charge density, where D is epsilon E, epsilon being permittivity, and E is negative grad V. So the part of this that breaks down now is the middle part, still in a dielectric. Within dielectrics, which are piezoelectrics, you generally don't have free charge density, so we'll be okay to say div of D is equal to 0, except possibly in the contacts around the material. So the boundary, we could have D coming in from the outside, but there's no divergence of D within the material. But with D, instead of being equal to epsilon E, D is going to equal the maybe piezoelectric D matrix times sigma plus epsilon TE, or maybe using the other form, we're going to say that D is the E matrix times the strain epsilon vector plus epsilon permittivity times E. So instead of using the just raw linear dielectric relationship, we can still use the other two though. To recap that, if we know what the voltage is, then we can find out the electric field and then just solve the first equation from either of these sets by itself, and then go and solve the second equation by itself once we've got the results of the first equation. It's like, it's not really a coupled set of equations, it's more one that leads directly to the other if we already know what the voltage is and therefore the electric field. If, though, we don't, if we have to solve for what the D field is, we can at least use the fact that the divergence of D is 0 inside of the dielectric because there's no free charge there. And in some special cases, we'll be able to say that just D is equal to 0. When does that happen? Well, there's no free charge inside the dielectric, so there's no divergence there. So if we have just a dielectric in otherwise empty space, then there's no D field at all, and we'll be able to say that the D in the second equation is equal to 0, and use that to solve for the E, make a more combined equation that we can then use to solve for the stress and strain and subsequently the voltage. Up next, some relationships between the components. The compliance matrix and the stiffness matrix are inverses of each other, which we know from before. That's still going to be the case. And the piezoelectric D and E matrices are related by the stiffness or compliance matrix. And then the permittivities are related through the piezoelectric matrices. Let's work out how you can figure this stuff out. So we're going to start with the stress charge and strain charge form of the constitutive equations here. And now let's say that the electric field is equal to 0. If we know somewhere that the electric field is equal to 0, maybe because we've grounded the whole thing, then we have that sigma is equal to C times the epsilon vector. And the other equation says that epsilon has to equal S times sigma. Okay, but sigma was equal to C times epsilon. So epsilon is equal to S times C times itself for any value of the strain, which means that SC has to equal the identity matrix, and therefore S is equal to C inverse and vice versa. Okay, that's the first one. The compliance matrix is the inverse of the stiffness matrix. Right, what's the next one? So now we're going to look for a relationship between the piezoelectric coefficients. And the way that we can do this one is by taking a taking another substitution through this, except this time we are going to imagine that, let's say the stress is 0. So let's imagine that it's a free material. If it's a free material, then we have that C times epsilon is equal to E transpose times E, while in the first equation of the second set here, we've got that epsilon itself is equal to D transpose times E. And now, let's see, we could substitute this one into this first one. Maybe I'll write that in the other order to make that a bit easier to see. So C epsilon is equal to this. Actually, let's even rearrange even further. So still with us? Still with me here? We've got E is equal, epsilon vector is equal to D transpose E in the event that sigma 0. And sigma 0 in this one allows us to rearrange E transpose times the electric field is equal to the stiffness times the strain. Okay, now we substitute in the strain, and we've got that it's stiffness times D transpose E. For this to be true for any electric field, we need that E transpose is equal to C times D transpose. And that means, taking a transpose of everything, that E is equal to C D transpose transpose. And you might remember that when you transpose a product of matrices, you have to reverse them on the inside. Otherwise, the matrix product won't even make sense anymore, right? Like you can see that that works for this one. We have to turn this into D transpose transpose, which is just D, times C transpose, but C is symmetric, so that's just C. For this matrix product to even work, C is a 6 by 6, D is a 6 by D is a 3 by 6 rather. D transpose is a 6 by 3. So C is C 6 by 6 multiplied by a 6 by 3 will be a 6 by 3 as a result. So you take the transpose of it and you get a 3 by 6, which is what E is supposed to be. Okay, now let's check that this works. 3 by 6 should be equal to a 3 by 6 times a 6 by 6. That's allowed, and it does give us the right size at the end. Okay, so there we go. There's E related to D and C. Or by right multiplying, have to keep the order consistent, by the inverse of C, we can figure out what the D matrix is from the E matrix. All right, finally, let's go and figure out how to relate the permittivities together. So if we've got that D is equal to, let's say, E times epsilon plus epsilon S times E, we can substitute in the other expression for D to get an expression that both of the epsilons are in. And then we'll have D times sigma plus epsilon T times E is equal to E times epsilon plus epsilon S times E. And then what else can we do? We can relate how the stress and strain are related together. So let's say that we're going to say that sigma is yeah, sure, let's sub in for sigma. Sigma is C times epsilon minus E transpose E. And here is the thing. This is supposed to work all the time, no matter what epsilon is, which means, no matter what the strain is, that is, which means it should also work if we have a strain of 0. So that is, we have a fixed object. So we have no strain on this thing, and that means we are going to get a 0 there and a 0 there, and we're going to be left with negative D E transpose times E plus epsilon T times E equals epsilon S times E. And therefore, epsilon S is equal to epsilon T minus DE transpose. Or epsilon T is equal to epsilon S plus DE transpose. Yeah, so just as a check, this is a 3 by 3, and we've got a 3 by 6 times a 6 by 3 now, and that's going to solve everything out. Yeah. Ta-da. So you'll notice maybe that this seems like it's not quite the same as what we got here. However, the transpose can be distributed across a sum, and these matrices for permittivity are symmetric. So that means that we also could equivalently write this as that plus the transpose of D times E transpose, which is going to be E transpose transpose, so E multiplied by D transpose. And there we go, same thing. This shows you how to relate the different components together, which is convenient because oftentimes you'll be given a set of material parameters in just one set of components. So this next section has the material parameters, the full matrices for alpha quartz, that's the piezoelectric quartz. The permittivity is only given in epsilon T form. If you need the epsilon S form, you'll have to go back to this this relationship and then solve for it using E and D. But how do you get D? Well, you're given D. How do you get E? You go back up to this relationship and say, all right, then E is equal to D right multiplied by the stiffness matrix. But we don't even have that. We've got the compliance matrix. So we first have to invert this, then we can take what we got and right multiply D by that to get E, and then we can take E and D, multiply them by each other after transposing one of them, and use that to get the other epsilon. So besides quartz, here's the matrix set for PZT5A. This is the compliance matrix for PZT5A. Doesn't seem nearly as asymmetric as quartz is. Quartz has these off-axis components, so axial components leading to shear and shear components leading to different shear through these things, which are hallmarks of asymmetric materials. PZT is not quite as asymmetric as quartz in that respect, but interestingly, just about as asymmetric seeming in the X and Y domain only as quartz is. And in the coupling coefficient matrix, we've seen this already for PZT, compared to quartz, similar kind of looking, but arranged differently. It's Z fields that do the stuff in PZT rather than X fields in quartz, and we don't have any coupling into Z in quartz. PZT is, it turns out, an even weirder material by being fully ferroelectric rather than just piezoelectric like quartz. So let's redo this example that we did analytically and see if we can get this same example to reproduce the strains we found earlier, except this time reproducing those strains by using FlexPDE to calculate this piezoelectric stuff. Okay, we will start with a setup that is for some thermal expansion type thing. So this is a set of matrix components that we had when we were looking at Voigt notation a long time ago. This is just some random material possibly was made up, and thermal expansion stuff. And let's see what it does. Does this simulation actually run and do things? Yes, it goes and does things, and that's great. We've got some strain as a result of it. Now we're going to turn all of that off. We're going to get rid of it, get rid of the thermal expansion, and replace it with some piezoelectricity. So the mechanical strain, rather than being the actual, the regular strain and then subtracting off the alpha times the temperature change, we're going to be subtracting off the piezoelectric effect. So piezoelectric effect from our constitutive equations is going to be the transpose of the D matrix minus D, so 1, 3 times E. Now, we have to choose something carefully here to not run into the rest of the symbols. We could call it just E field. We could call it EX, EY, EZ. That's probably going to get confusing because we already used EX, EY, and EZ for the strain components. So let's keep it as simple as possible, less likely to make a mistake this way. D13 times E field X plus, oh, not 13, what am I doing? D11 times E field X plus D12 E field Y plus D13 E field Z. Except, well, that's sort of what it would be if it wasn't for the fact that we're transposing this first. So this D11 component, yes, will be multiplied by E field X, but it's the D21 component that gets multiplied by the Y field to give us the new X component, and the 3-1 component that gets multiplied by the Z field. Okay. So we'll get something similar to this in all the different directions, except that it's the column that ends up getting changed. 2, 3, 4, 5, 6, and 6, 5, 4, 3, 2, 2, 3, 4, 5, 6. Okay, so there we go. Now we've got piezoelectric strain built in. We should be able to specify what the D components are for PZT. And we've got D11 is equal to 0, D12 is 0, D13 is 0, D14 is 0, D15 is 584, E minus 12, D16 is 0, 21, 0, 22 is 0, 23 is 0, D24 is 584, E minus 12 again, D25 is 0. So the white space doesn't matter in FlexPDE. We can lay it out like this to make it easier to see that we haven't missed anything. And D26 is 0. D31 is 0. D32 is 0. Oh, what am I doing? D31 is negative 171, E minus 12. D32 is negative 171, E minus 12. D33 is 374, E minus 12. Maybe we can say D32 is D31. And then lay these out with enough tabs to make them line up a bit better. Okay, D34 is 0. D35 is 0. D36 is 0. Okay, so now we can check across E minus 12, same thing as there. E minus 12, 584, 584, E minus 12. Okay, looks good. Much easier to check that we've got it in there correctly by laying it out in a way that looks kind of similar to this. And then we can also look across and make sure we typed all the components correctly. So we've got first column, second, third, fourth, fifth, sixth, and then 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, looks good. So let's check if everything else is correct. We need to have no load in any of the directions. So just apply this default one and get rid of this S applied thing that was in there from the previous simulation. And we should be able to get the same strains as we were expecting now if we also were to say what the E field is. E field X is 0. E field Y is 0. E field Z is equal to negative 1 E5. Okay. So first we have the correct strains showing up as we, or at least we have the, oh, these are 0. Right. Yeah, so compared to this one for the E field that we put in, we have the correct strains showing up. 1.71 E minus 5 is 171 E minus 7 in X, Y, and Z. And we've got 0 strains in the shear directions. And we also have a visual representation of what this looks like. So it's straining more in Z than it is in X and Y. It's getting narrower in X and Y than it is in Z. This is exaggerating it with quite a bit of magnification to show us what the size change in a cube of this would be. We didn't put it in the same dimensions as we actually were given up there. Okay, the next part is to try to modify FlexPDE further to determine the charge displacement field, D, and the charge on each plate using this. Right, so yes, let's give it a shot. To figure out the charge on each plate, we can, well, there's a couple of different things that we might do here. We can directly still leave the electric field as it is, and now that we know the electric field, we can compute what the D field is. So we'll say E field is a vector. Is this worth doing? Maybe. Let's, not yet. Okay, so we'll say that the D field, now we'll put it down after we've got the stresses down there. D field is equal to a vector of D field 1, D field 2, let's just use D field X, Y, D field Z, and then we'll say that those things, D field X, comes from multiplying the D matrix by sigma and then adding epsilon times E. So we're going to need to have the D matrix multiplied by the stress being this this 6-dimensional thing here. So there's going to be a lot of typing out here. We're going to have D in its natural form. We don't have to worry about any transpose type stuff. D11 times SX plus D12 times SY plus D13 times SZ plus D14 times SYZ plus D15 times SXZ plus D16 times SXY. Right. Yes. So this one, not quite so bad. D field Y, D field Z, 2131, and then doing the same thing for the rest of the components. And we've got it. Okay, so there's our D field. Except that we also need to add in what the epsilon T is. Epsilon T 11 for PZT. We can go back up to this parameter, this set of parameters here. Epsilon naught is equal to 0. Sorry, what am I doing? 8.85 E minus 12. We'll make it. We're getting there. Epsilon T 11 is equal to epsilon naught times 1730. Epsilon T 22 is epsilon naught times 1730. Epsilon T 33 is epsilon naught times 1700. Okay, now we've got the epsilons in there, and so we can modify this to account for there being an electric field by adding in the diagonal components of epsilon, which are the only non-zero components of epsilon because it's a diagonal matrix, this permittivity. Epsilon T11 times E field X and epsilon T22 E field Y, then epsilon T33 times E field Z. Yeah. Okay. So we shouldn't have messed anything up yet. Great. And now we can report val similar to these ones. Sure, the middle's fine. D field X, D field Y, and D field Z. Let's see what it is. So it looks like the D field is very nearly 0 in the X and Y directions and is non-zero in the Z direction, quite a lot higher in the Z direction. So what's going on there? Why is it a lot higher in the Z direction? The D field is based on the stress and is based on the electric field. So we don't have stress in any other directions from the setup that we have right here. And we have an electric field that is only in the Z direction. So that explains why the D field is only going to be in the Z direction here. Now you might be wondering, what if instead of this, okay, that's great there, Dr. Minnick, but what about, we've got a different formula for the D field. Sure, your formula here is only based on stress, but I've got this other black market formula for the D field that puts it in terms of strain there. What do you think of that? Well, yeah, that would be a different one, right? So now we're going to have to figure out, before we use this, what epsilon S is and what E are, and see whether or not we get exactly the same thing. So to check out these formulas and see whether or not they actually, the other one actually works, what we can do is first figure out these coefficients in Maple to compare with. Okay, you could use whatever computer algebra system you like to do that. First, we are going to need to figure out what E is. And before we do that, we're going to need to figure out, we're going to need to get the compliance matrix and the stiffness matrix into these equations. So let's include linear algebra just so we can take matrix inverses, and then we'll type in the components that we've got for PZT. S is matrix 16.4, negative 5.74, negative 7.22, 0, 0, 0. Shift enter to go to the next line. Negative 5.74, 16.4, negative 7.22, 0, 0, 0. And same thing, negative 7.22, negative 7.22, and 18.8, 0, 0, 0. And then 0, 0, 0, 47.5, 0, 0, 0, 0, 0, 0, 47.5, 0, and 0, 0, 0, 0, 0, 44.3. Now let's check, does that look the same? Yes, seems good. Okay, now that is times 10 to the negative 12, actually, which makes it look like a gross mess of decimals. So let's not report it. It's still there. We're still calculating it. We're just not going to display that answer. Okay, D. Can I use D? Yeah, of course I can. Okay, this isn't FlexPDE here. I can make a variable named D. Okay, so D is equal to matrix of 0, 0, 0, 0, 584, 0, 0, 0, 0, 584, 0, 0, and negative 171, negative 171, 374, 0, 0, 0. And again, let's have a look at that. Looks good. Now we'll put in times 1 e minus 12 again. And because it gets gross, we're going to stop reporting that too. Final thing, epsilon t is equal to a matrix of 1730, 0, 0, 0, 1730, 0, 0, 0, 1700. And we got that. Okay. Now we're going to multiply this by epsilon naught, where epsilon naught is 8.85, e minus 12. Okay. Fantastic. So next thing to do is to check out those, the relationships between the different components. In fact, before we even do that, we could probably check out the strain that we calculated for this electric field and see that it worked out. So we've got the electric field, E field, is equal to 0, 0, negative 100 E3, And now from that, we should be able to figure out what the strain is, given also that sigma is equal to 0, 0, 0, 0, 0, 0. This is a free object this time. Okay, so no stress, and we've got that strain that's just in the electric field that's just in the z direction. So the first piezoelectric, the piezoelectric coupling coefficient matrix that we have is going to allow us to figure out what the strain is in this strain charge form. Regular epsilon, vector epsilon, the strain, is equal to S dot sigma plus D transpose dot E. So is this going to work? No, not really, because we don't, well, we don't actually know what S is. Oh, no, we do. We've got S written up there. What am I talking about? We've got S, so we're going to multiply that by sigma, and we get 0. Fine. We've got the transpose of D, but we put in the wrong name here. So it didn't work, but for a totally different reason. Transpose of D times the E field. Okay, there we go. So this is kind of nice. By typing in the matrix things, you can just deal with these, with the sort of problem that we have when everything's uniform, at least. Maple can solve it just fine. We do this this vector algebra here without many issues, and we've got what the strain is, just like we calculated. Okay, next step, we can figure out what the D field is. D field is supposed to equal D dot sigma plus epsilon T dot E field. Okay, and that's what we calculated as well. That's the negative 1.5 E minus 3, 5045 even. Wow, quite accurate. Well, that's not surprising. I guess this one we just multiplied out directly. We just wrote out the matrix multiplication directly rather than solved a differential equation to find that one. So that's not so surprising. So we verified that the D field agrees with what we had in FlexPDE using the same kind of calculation, but the thing that was a little bit weird about that calculation in FlexPDE is that it didn't rely on is that the stress was equal to 0, so we had nothing showing up in the other dimensions. How can it be that we have non-zero strain in all the dimensions, but we get only a charge displacement field in the z direction from this equation? Well, let's go and figure out what this E coupling coefficient is. To be able to do that, we've got to take the D field, we've got to take the D matrix that we have and right multiply it by C. So we need to find the stiffness matrix, C. First, C is matrix inverse of S. And this is kind of gross. You can clean it up by expressing it in gigapascals. So now it looks a little bit nicer. Divide by 1e9 to see how many gigapascals the thing was. Anyway, we'll just take C as the regular one. Without doing that, we'll put it in its regular units and just won't display it. So now that we've got C, we can find E, the E matrix, which we probably cannot assign to in Maple. Let's see. E is 7. Does it let us do that? Apparently it does. Okay, so we're going to take E and get it by taking D and right multiplying by C. Okay, so this is kind of interesting. We didn't scale this, right? D is in units of 10 to the negative 12. And C is in units of around 10 to the 12. So when you multiply them together, you get units around 1. So what we have here for the E matrix is something that has the same kind of components as the D matrix does for PZT. So it's got zeros in all the places that the D matrix for PZT does, but it has different values for those components. And now let's see what happens when we try and find out what epsilon s is. Epsilon s will be equal to epsilon t minus E dot transpose of D. Okay, so epsilon s, also diagonal as promised, has different components than epsilon t. Being, in the case of this PZT5A, possessing components that are about half as big as epsilon t was. So it's not so obvious how this is all going to work out, right? Like, how is it that we are going to have strains in X and Y for this original material, and yet when we take E and multiply by the non-zero strain rather than multiply D by the zero stress vector, we're still going to have zeros in the X and Y components? Well, let's explore that. Let's take E dot epsilon. Let's multiply this thing by the strain vector and see what goes on. It has zeros in the first two components. Why? Well, E ended up, for the case of PZT, where do those first two components come from? It comes from the first two rows of E being multiplied by the electric field. So even though the or rather this thing being multiplied by the strain, the strain here. So E, its first two rows multiplied by the strain. Even though the strain is non-zero, the first two rows have totally zero components in the first three columns, meaning that there's no coupling of axial strains to charge displacements in X and Y. The E field, I keep saying field, the E matrix here, the E matrix tells you about how you get electric displacement fields based on strains. So strains by themselves in any direction, in axial X or axial Y, don't lead to any charge displacement in the X or Y directions. But strains in the X or the Y or the Z direction can, in PZT, lead to charge displacements in Z. So any strain leads to charge displacement in Z, any axial strain. You can get charge displacement in X and Y in PZT, but to do it, you've got to put the crystal into some shear strain somehow. So that's what's going on in these two components. You've got to put it into shear XZ or shear YZ in order to get that to happen. Now we can explore that, but before we do, we'd better make sure to correct an oversight that we had earlier, which hasn't actually mattered yet. And that is, we never actually put in the stiffness matrix components for PZT. And yet, we still were getting the right answers. We were still getting exactly the strains that we were predicting. This is because we're dealing with a totally free object. And as expected, the stiffness matrix components shouldn't actually matter for a totally free object. Nothing is resisting anything in the stiffness direction. So now, finally, we will need to put this in. This is, these are easiest to enter when you've first divided by 1E9 to put it into gigapascals, as we saw earlier. Okay, so now that we've got this in gigapascals, we can go ahead the business of typing in the C components. So this is 120.3, 75.18, 75.09, and this one is 0, 0, 0. We'll just zero these off-axis components now before I forget. Okay, next unique entry, 120. Again, this is going to be C11. And then here we've got C13, 110.867 E9. 3.4 is 0 and all that. 4.4 is actually pretty close, 21.05 E9. 21.05 E9 again. Maybe we'll just copy the component, C44. And then finally, 22.57 E9. Now this should change nothing. Let's just check. Nothing's changed yet. Okay, all good. And now let's see if we can apply some boundary conditions, which should lead to an x-directed electric field. So if we are understanding everything correctly, or not x-directed electric field, an x-directed charge displacement, we should be able to get a charge displacement even if the electric field isn't leading to anything in x, if we were to apply the appropriate strain to this material. And that strain that will do it is an XZ strain. Now, we can get an XZ strain happening in this by taking on the bottom surface, load U is S applied, I think we called it earlier. We have this applied stress ready to go, 1 megapascal. I'd say compressive, but we're going to apply a shear stress, so negative 1 megapascal stress. And on the top, I guess we'll do negative there, and then S applied there. And then on the X surfaces, we'll say load of W is equal to S applied. We'll take that away over here. And then over here, load of W is equal to negative S applied. Now with no constraints to stop the thing from flying off to infinity. We might have the thing running away, but let's just see if we're lucky. Okay, it looks good. Didn't run away. And indeed, look at this. We've got a non-zero component for the X part of the D field now, just through applying that strain as expected. So we applied applying the stress as expected. Another thing we could have done is perhaps applied a strain directly, right? How could we apply a strain directly? Well, we could have said on the bottom surface, value of U is 0. And then on the top surface, value of U is 0.001. And then we'll just leave the loads as 0 on the other surfaces. Now this isn't a pure strain. This is going to cause probably some curving on the sides. Let's see if we can get this to work. So it can't move on one Z surface on the back there, but then it moves a little bit more on the other Z surface in X. So on the bottom Z surface, it's fixed to one thing in X. On the other Z surface, it's fixed to that in X. And yeah, there we go. So we're getting some XZ strain showing up now, and we have some component, but it's pretty small. I wonder if this is actually rotating a bit. Seems like it probably is just rotating a bit. Let's see if we can stop that. So how would we stop it from rotating? Well, we'll say on the X surfaces, value of W equals 0.001. Load of W is 0. And then value of W is equal to 0 on the bottom X surface. So now we're going to force it to shear. Aha. There we go. Now it's actually working. So before, when we only applied on the bottom surface a certain value of X displacement and on the top surface a different one, it was accomplishing it by rotating. To fix that, we can make it on the bottom surface fixed in Z, and then on the top surface have a or rather on the back surface here, the low X have a certain Z displacement, and then on the other surface have another fixed Z displacement. So we make it hold still here and move up on this side. And then on the bottom, we make it hold still in X and move to the right on the top, and that forces it into pure shear. So with that applied, we now have a very large D field in the X direction by the now guaranteed XZ shear that we've forced this thing into. Okay, so last little bit on this is how do we figure out what the charge displacement is, what the actual physical charge is that's shown up from the charge displacement field. The way to do that is to remember what the charge displacement field is. It's the divergence of the charge density. So if we imagine back to the simpler case, when we are just applying a voltage on the top and the bottom of this plate, then that we've got some voltage applied, this voltage applied by applying a charge on the top of it and another charge on the bottom of it, we can figure out what the charge that must be on the top of this plate is by looking at the D field around the top of the plate. So that is, we can add up all the charge that has to be on the top plate with respect to volume over the top plate by integrating over some region that includes the top plate. We don't have to do just the top plate. If we say the charge density inside the dielectric around it is 0 and the charge density right around that top capacitor plate is equal to 0, then we can integrate over that stuff too, and it should be the same as integrating over just this top plate. And now if rho f is the divergence of the electric displacement field, we could, instead of doing that integral, we could do an area integral using the divergence theorem of d dot ds, outward flux of the electric displacement field over the boundary of the top plate, or at least the region around the top plate. Now, if this is an otherwise empty space, there won't be any electric displacement field except between the plates here. So the electric displacement field roughly outside of this this thing is still quite thin. It's a lot like a capacitor in geometry. The electric field and the charge displacement field outside are going to be 0. There's no piezoelectric out here. We've just got a permittivity of free space. So the electric field is 0 outside, and so is the charge displacement field. So that means that we don't really have to integrate around the entire boundary of the top plate plus. We can just integrate d over just this interior part, and that's where d is going to be uniform. So over the, let's say the interior, over the mid maybe, and this is, we reason that the d field has to point generally in the same direction as the e field in the absence of funky stress type stuff that's doing that, or certainly we only care about the one that's perpendicular to this surface if we pick this area there. So we really just care about the d in the z direction. And that is, anyway, d dotted with the z direction here is going to tell us what the total charge is. So we could integrate d dotted with ds over this cross-sectional plane here slicing through the thing, and that should tell us how much total charge is on that top plate. So this is going to be the d in the interior times the area, as long as d is really just in the z direction. Okay, so that allows us to figure out what the charge is that's on the top plate by looking at what the size of the polarization field is. So when we had a polarization field in the z direction of this 1.4 e minus 3, when we multiply that by the 5 centimeters and the 1 centimeter, we can figure out how many coulombs of charge are on the top plate. So we'll say report val d field z times L x times Ly at Lx over 2, Ly over 2, and Lz over 2, which works as long as d field z is uniform, as Q top. Right, so this is the number of coulombs on the top plate. So 1.4 for E minus 5, it tells us, oh yes, so D field Z should be in the negative direction here. So if we go negative D field Z, that's the amount down. That would be the amount of charge that's enclosed by an area that's enclosing the top plate. And there we go. So we have positive charge on the top because D field Z is negative. Piezoelectric bimorphs, just like with thermal bimorphs, it's possible to heat up thin layers of piezoelectric material and induce different longitudinal strain in each layer to cause curvature according to this formula. This is the same as it was for thermal curvature, added to the moment-induced curvature, except now we've got the source of the internal strain is the piezoelectric effect. This is, if x is the length direction, you'd have the piezoelectric strain in the x direction, longitudinal direction. You use the E, the stiffness, in the length direction, effective stiffness in the length direction, given what's going on in the other directions. And this is if the beam is thin in y and we're looking at the bending in the y direction, that shows up as a result of this perhaps different piezoelectric expansion at different positions in y. Okay, so EI, as before, is flexural rigidity for bending in the y direction. Piezoelectric strain in the x direction would be by multiplying D transpose times E and taking the first component to get the x strain. You'd have D11 EX plus D21 EY plus D31 EZ. Okay. Now, as before, with these multimorphs, we want to make the length to thickness ratio as high as possible to maximize the tip deflection when we have something that's really thin, and then we put a little bit of different strain in the top and the bottom, then we can get a lot of curvature and get a lot of deflection if the beam is also long. In addition, we want to use the largest electric field possible to get the biggest signal, because this is going to be bigger if we have a bigger E field. And because E is the negative gradient of V, and we're generally applying voltage rather than electric field directly, we can get the biggest E field if we have the thinnest separation between the plates where we're applying a voltage. So we want to set this up so that we get one of these perpendicular direction piezoelectric strain effects. For example, we apply an electric field in the X direction and then get a strain in the y direction. Or maybe if an electric field in the y direction will lead to strain in x, then that's how we'd set it up. Yeah, we want to have this direction be one where the electric field will lead to a strain in this direction. So that's how we want to set up these multimorphs. All right, so let's have a look at this for PZT5A in particular. Imagine we're going to set it up like this. We've got two identical PZT5A stacks, and their orientation is lined up with the crystal direction. We have to figure out which way to put a contact through this thing in the top and the bottom and in the middle. Like, which way should we have the field applied across in the crystal in order to get the maximum curvature, maximum tip displacement if we're going to fix it at one end? Well, for PZT, we have seen that it's the Z field that leads to axial strains, and we're able to get axial strains in X or Y or in Z. So it's up to us whichever one we want to pick for the length direction. Totally up to us. So let's make Z the thickness direction, and let's make Y the length direction. Totally arbitrary, could have picked X, but it is important that Z be the thickness direction to maximize the displacement. So that's what we pick, and that's why. Because we have Z fields coupling to axial strains in the other direction, we have to have Z be the thickness direction so we can apply a really large electric field by having the thin dimension of the thickness direction in a bimorph leading to large fields. And then we need the strain from those fields to show up in the length direction, so we have to pick either X or Y for that. Next, we're going to figure out what the tip displacement should be. If Vmax is 100 volts, the total thickness is 1 millimeter, the width is 4 millimeters, and the length is 2 centimeters. So we've got a symmetric one. So we've got half of the thickness on the bottom, half of the thickness on the top. We're going to use this formula, and the E is going to be the effective stiffness in the length direction. Now, you might remember that effective stiffness is how stress and strain are related, and since we have the beam being otherwise free pretty much, except maybe at the anchors, the effective stiffness is going to be in the effective stiffness in the X or Y direction, whichever one we're going to say is length, let's say Y, is 1 over the S component in that direction, 1 over the compliance matrix component in that direction. So first thing, we're going to say that E, this is the stiffness, is 1 over 16.4 E minus 12. That is the effective Young's modulus for PZT in the length direction. Next thing we're going to need the coupling coefficient of the electric field in the Z direction to the strain in the length direction. And for us, that's D32. D32 is negative 171 E minus 12. And then we're going to need to know what Vmax is. Vmax is 100. And the thickness is H over 2, where H is equal to 1 E minus 3. And we're also given what B is. B is 4 E minus 3, and L is 2 E minus 2. Okay, so next up, we need to determine what Y bar is. And E is not location dependent, so it's just going to come out of the integral, but we can put in the full formula anyway. Y bar would be equal to the integral of the integral over the cross section. And actually, we shouldn't say Y bar, because we've got the thickness direction isn't Y anymore. Thickness direction is Z. So Z bar would be the integral of the integral over the cross section. We're extending in Y, so it's an integral of E times Z from Z is, let's see, what's the low value of this? We're going to say, in the notes, I go from negative H over 2 to H over 2, and I put Z equals 0 in the middle. Let's set it up differently. Let's just go from 0 to H. Okay, so Z is 0 to H, and then we're going to take X is equal to 0 on the range from 0 to B. So we expect that Z bar should just be in the middle of H, which, ooh, something clearly has gone wrong here. Ah, right. So we didn't divide by the same integrals, but of just E. Right. Okay, there we go. So Z bar is half of a millimeter up. Not surprising. Next thing, we're going to figure out what EI is. So EI is the same integrals except of Z minus Z bar all squared, and this time no dividing. So this is flexural rigidity. It's not very large because the beam is quite small. So with only 1 millimeter of thickness, the flexural rigidity is pretty small for this thing. Okay, this is for bending about the X direction for this thing. So this is bending in the Z, in Z. Yeah. So next thing, we can figure out the curvature after we have also put in what the piezoelectric strain is in the length direction, which for us is Y. So epsilon piezo in the Y direction is equal to a piecewise function. If Z is less than H over 2, then we're going to have the electric field down here. You know, actually, I suppose it's probably how to lay this out. Maybe we'll say instead that the piecewise function is the electric field. So E field in the Z is piecewise. If Z is less than H over 2, then we've got an electric field that points down. And this is going to be negative Vmax over H over 2. If Z is greater than H over 2, then we're going to go Vmax over H over 2. All right, so there's our E field. Depends on what Z is. And then we're going to say the piezoelectric strain in the Y direction is D32 times E field Z. Regardless of what Z we're at, it's fair to say that you multiply the E field there by D32, and you've got the piezoelectric strain showing up in the Y direction if the thing is otherwise free. And there's, yeah, actually that's fair. Even if it isn't free, that would be the piezoelectric strain. Okay. Yes, next. Now we've got the curvature. C is equal to negative 1 over EI times the integral of E times Z minus Z bar, not squared this time, times EP piezo Y from Z equals 0 to H, and X is equal to X running from 0 to B. Okay, so we've got a curvature of 0.103. And we can mess around with these things and see if some numbers make sense for us. So let's just see how much can we actually calculate if we don't tell it the material parameters. All right, how far can we get in this thing? Interesting. So if H is less than 0, it's not, it's 1. Then we're going to have a 1 up here. H is greater than 0, so we've got a 1 there. This is just the same term as this one, but with a half. So it looks like we're going to have overall a minus 6 times E times D32 V max HB over E times B times H cubed, which if we were to simplify when H is positive is going to turn into the E's canceling. The Vmax sticks around, D32 sticks around, B cancels, and we've got a D32 Vmax over H squared. Right. Which means, I mean, one way to check that this is actually, that this is correct here is if we were to take this curvature and we were to multiply by the inverse of that, H squared times Vmax, let's put this on a new line, C times H squared over D32 times Vmax times 6, then we should get -1. Aha. Okay, so it worked. The scaling is correct. So this is the inverse of the curvature. Maybe to make it more clear, we'll do divide by D32 Vmax times 6 over H squared. So that should be the same size as the curvature. Yeah. So this is the curvature that shows up, negative D32 Vmax times 6 over H squared. You see the sorts of things that it depends on. Curvature doesn't depend on the length or the width as it shouldn't. And when we've got a symmetric bimorph, the thinner you make it, rather than going inverse with H, like things went before, like the thickness for the thermal bimorphs, because the thinness of this cantilever will also lead to more electric field for the same voltage. The H shows up in there twice, and this scales twice as fast as you decrease the thickness of it. That said, it is harder and harder to, I don't know, well, not harder and harder. It's more, let's say the limit of the voltage you can apply also goes down as you make things thinner. It's the thinner it is, the less voltage it can take before the electric field gets to the breakdown field. Okay, so because of this scaling, the same voltage will produce a lot more curvature for thinner multimorphs. So final thing to do is to check this in FlexPDE. Let's build in the dimensions that we've got. We've already got the PZT material substituted into there, so we can just change the dimensions to the ones that we were given in this problem. So we're going to have the thickness be the z direction, 1e minus 3. The length we said was y, which is 2e minus 2, and the width is b, so this is width is x, I should say, 4e minus 3. Okay. And then what we're going to try to do is get rid of this applied stress, get rid of the other boundary conditions that we were doing in here. Put it to a load of 0 everywhere, except for the x equals 0, or no, the y equals 0 surface. That's our fixed surface. Then we're going to need to change what's going on in z a bit. So we'll say we'll add a mid surface. Actually, let's first not do this and then see if it makes much of a difference. Right. So what we'll do is we'll change the electric field to be this piecewise thing, which in FlexPDE would do with an if statement. If z is less than Lz over 2, then we're going to need a negative field, negative 100 over Lz over 2. Let's put in Vmax. Else Vmax over Lz over 2. Okay, so that should allow us to get a little beam here, and then hopefully it's going to curve. Yeah, okay, great. So there's the beam, there's the curving of that beam. We can try to rotate it and see what's going on. Did it. Got some piezoelectric bimorph stuff happening. To be able to compare this with maple, we're going to need to figure out the tip displacement here and figure out that tip displacement in maple and compare them. So since the beam is bending in Z, we're going to report val of W at the end, which is going to be Lx over 2, the middle of the end, let's say, Ly, and Lz over 2, because we stacked it this time from 0 to Lz. And the tip displacement we get there, we can compare with C times, oh, I seem to have crashed FlexPDE. Let's try that again. Fortunately, it saves every time between simulations. So let's try that out. Maybe I won't type over here while I'm doing that this time. Yeah, okay, so we've got negative 2e minus 5, and let's see, c times 0.5 times L squared gives us 2e minus 5. Okay, so pretty good. The what's the difference? We've got a negative where maybe we weren't expecting a negative before. So the curvature that we calculated in maple was positive, while the curvature that we calculated in FlexPDE, or the tip displacement in maple is positive, tip displacement in FlexPDE seems to be negative. What's going on there? Why would it be negative for one and positive for the other one? Aha! There was a problem when we put in the D field in not the D field, the electric field, adding multiplied by the coupling coefficient matrix in FlexPDE earlier. Maybe you can see it right here. We meant to say minus these things in brackets, right? Minus that in brackets. Otherwise, the negative doesn't carry across, and we end up getting the right answer only when we're only applying electric fields in X. So I suppose that the answers have been kind of backwards the whole time, and nobody noticed, or maybe you noticed. In case you did, good for you. But yeah, I suppose this is if we had a negative Z field when before we were supposed to have a positive Z field, that would be why the strain was negative, what it was before. So this is going to now reverse the direction of this, bending up, because we're not missing that sign anymore, and that would be something that we'd want to fix in the work that you do as well, just to make sure that that stuff works. Okay, so what caught that is comparing Maple to FlexPDE. Easy to make that kind of mistake, and I just can't stress validation enough. You know, you got to validate the stuff if you want to be sure that it's actually working. Okay, so what we did is build some piezoelectric bimorphs and calculate how they should work, and then also show how they work in FlexPDE.